So my name is Larg Weiland. I'm with PDF Solutions, and I'm here today to talk about a prototype I developed for web-based open access viewer using Go. I'm not sure you heard about Go. Everyone knows Go? You know Go? So Go is a language developed by Google, and I will tell you a little bit more about it. It's kind of interesting, especially for this use case. Okay? So the talk is structured in the following way. Give you a little bit background about what we are, what PDF Solution does. Then I talk about the concept of the idea, give you a quick introduction into Go, and then also into Twix, which is needed in this case to be able to access open access data from Go, and then about the idea, how the web server was set up, what tools we used to handle polygon data, zooming in, zooming out, delayering, and so forth, and then some conclusions. Okay, PDF Solution at a glance. So our mission is develop and commercialize semiconductor electrical characterization ecosystem that is co-optimized design and fabrication that results in lower cost, higher yield, and better performance. What technology are we using for that? We have proprietary electrical characterization test structures, proprietary analysis software, measurement hardware, as well as big data analytics software and design IP. What are we offering our customers is solutions for accelerating fab yield ramp, electrical characterization for production control, Extensio big data analytics software for fabless, foundries, test and assembly, production control and monitoring. I go a little bit more in detail on the next slide. What are our customers? Are typically logic and memory foundries, fabless semiconductor companies, intellectual property providers, test and assembly houses, and system OEMs. So when you work with us, typically we provide a complete electrically probed and e-beam probed infrastructures, which we call CVI or DFI. Which is composed of proprietary test chips, test systems, which are electrically as well as e-beam, and entire analysis systems. What we call the characterization vehicle development system is kind of comprised of from DOE design to automated cell design, automated test program generation, automated documentation, and so forth. So we're dealing with lots of designs. We have typically about 100 tape-outs per year in technologies from 28 to 7 nanometer. So we have seen it all. We have seen the increase in complexity, especially, and I have a few words about that later in my talk. The DFI, or Design for Inspection System, this is something new we are working on where we provide an e-beam tool with our engagement. So we are not selling any tools, we are just providing this as part of our engagement, which allows us then to measure these things which we have on silicon way, way faster than every other tool on the market. So what DFI is, there are several ways. Take the latest pointer. So either we inject DFI structures in the form of scribe line structures or entire full reticle CVs. Or the other way is we inject structures into filler cells. So instead of using standard filler cells, we use our DFI structures. And that allows us to put billions, literally billions of little test chips onto your design, embedded in your product. And the e-beam tool then allows us to do almost real-time inspection of any kind of problems you have there. So in this talk, we focus about the need of a web-based reviewing system of DFI and CV designs. And the problem here is that, okay, there are designers, but other than designers, which are the only ones who can use a tool like Cadence. Other people have no idea what Cadence is or how to use an EDA tool, but they want to look at how these structures look. What is the DOE? How were they designed? How do they function? And you cannot expect from them to open a layout in Cadence. So you need something else. A web-based tool would be ideal, of course. And they have also different requirements. What a designer thinks it's cool in terms of colors and stipple pattern for layers, well, other people hate that. They want to have their own color view of a layout, right? They look at things completely different than a designer. And with a web-based system, you can all do this. You can have your own mapping of colors, stipples, the way you show layers, and so forth. So about the concept, so what I was thinking about, so we need to interface with the OpenAccess API through a web server. It's easier said than done, of course. Typically, oops, let me go. Here's the laser pointer. Okay, typically the standard way is you have a designer working with an EDA tool, whether it's Cadence or anything else out there, which goes through the OpenAccess API and talks to your OpenAccess database. So now we want to have something which talks to the OpenAccess database, but serves it on a web browser, and many, many people can just get access to it. The initial thought is, okay, OpenAccess is based on C++. Okay, let's keep that in mind. Then what are typical languages which deal with web browsing or serving? For instance, there's Rails, Ruby on Rails. It's great, but can it really handle polygon data fast enough? Is it the right platform? I don't know, maybe, maybe not. So the prototype I was thinking about, I heard something, or I was just playing with Go, and I was thinking, well, why not use Go? Why not? Let's see if it has any advantage over the other systems. And so we would use something like Go, interface with OpenAccess, and then some kind of Java script, and then serve it. Let's see how we can do that. Okay, why Go? Well, why not? We can do everything, right? So I was intrigued about, well, a web server you can write in one line of code. Great. One line of code, you have a web server. Done. Great. It has a big community, I have to say. It's the Redmond programming language ranking from this year says Go is number 15, so it's not too bad. C++ is 5 in comparison. Well, at least we are working on something which gets used. And if the inventor from Go, which is Google, uses it, it might be good. The other thing which sounded really appealing to me was concurrency inside Go. Go was built for concurrency, or with concurrency in mind. And that's kind of a cool idea. And where could we utilize this? Okay, we have multi-user access, of course. It's a web-based system. That might be handy. If we have large layouts, maybe we can do something like tiling it, breaking it down, and work concurrently in reading it, accessing it. So that might be helpful. Or we can even do cooler stuff by accessing instance data concurrently. Instead of reading it sequentially through the hierarchies of OpenAccess, we just do massively parallel. Give it 100 CPUs and let just rock. And that was the initial idea. Then I looked a little closer. What can we do with Go in terms of binding it to C++? It's not that simple. So the GC compiler, which is the standard Go compiler, is apparently different. It has a different calling convention and linkers, so you cannot do anything with C++. But luckily, these guys, Google guys, thought, well, they also have a CGO compiler, which can actually be linked with C. And if you use then Swig, which is a simplified wrapper and interface generator, you can extend this to C++ libraries. So that was the initial idea. Now, a brief introduction into Go. So GOlang, Go or GOlang was created 2007 by Google. Rob Pike et al. Was mainly drivers. You find everything about it at golang.org. Its current version is 1.8, so it came around when I was initially working on this idea. It was, I guess, a couple of years back, but I put it on ice for a while because there were some issues with web browsers at that time and so forth. So I did it with 1.1, I think, and it came quite a bit to 1.8. It's pretty stable now. They promise to not change grammar and anything like that anymore. So whatever you develop might even work in a couple of years from now. It's a compiled, statically typed language. It's very similar to C, so if you know C, you might be really happy with it because you can read it, you can understand it. So your standard Hello World example is you have to define a package, which, okay, it's main in this case. You import some kind of standard libraries you want to use, like the formatting package, and then you define a function called main, and you do fmt.println hello world, and you compile it, done. Works like a charm. Go is, unfortunately, we can argue about that, whether it's object-oriented or not. It's kind of not. It has many concepts. It mainly uses structs, like in C. So you have, for instance, in this example, you define a rectangle as a struct, which has x1, y1, x2, y2 as a float 64. And then you can define methods for these structs. So you would define an area function which only works on a rectangle, and that simply returns, in this case, a float 64, which is the area of this rectangle. Concurrent programming, as mentioned before, Go was built with concurrency in mind. And to write something concurrent in Go, the only thing you have to do is write Go and then your function. That pushes it off, and according to Google, these Go routines are super lightweight, so there's almost no overhead. You can run, and they claim you can run 1 million Go routines concurrently, and they can all talk to each other. So they use a method called channel, where they can talk to each other. You simply use a channel to move either synchronous or asynchronous data between channels, and that's a really cool feature. Very brief introduction to Swig. I don't want to make it too hard here, just so that you have heard it and for what it's used. So Swig is a simplified wrapper and interface generator. It connects programs and libraries which you have written in C or C++ to almost any scripting language, like Ruby, Perl, Python, you name it. It's really powerful in this sense. And you can also connect it to compiled languages, of course, like Go, Java, I mean, whatever is out there almost. You can call then from your language native functions written in C++. You can pass complex data back and forth. You can inherit object classes across languages if your target language is object-oriented, like Go is not. If we compare data types between C++ and Go, they are pretty close. I mean, you have bools, you have all sorts of different size integers like int 8s, 16s, 32s, and floats. So it maps pretty well from one language to another without any big hassle. Oops, no. That's really, oh, sorry, I went too much. So interesting enough, Swig is also used in OpenAccess, especially for OAScript and OAXPOP. If we are looking at OAScript, it reveals the complexity of using Swig to map an entire library like OpenAccess to any of the scripting language where it was used for. So there are lots of type maps. It's highly nested file structure. So if you really want to understand how this is done, this is really painful, I have to tell you. So I decided not to map everything to Go because it's just for this idea, it's not necessary. We don't need everything. The only thing we would need to map is something like that we can access an OpenAccess library, traverse the hierarchy, get all the information out we want to display, like rectangle, polygons, paths, so any kind of geometric object, maybe some additional layer information and some properties. That's pretty much it. And that we essentially make our own little wrapper, and that gets swigged to Go.
Larg,
yes?
How big is a few? Is it a dozen or 100?
It's what I have essentially one header file and one C++. It has maybe 5, 6 classes. So it's really small. It's not elegant. I will tell you later why not, but it works for the purpose of a prototype. Now let's talk about OA and thread safety. Because we said, okay, Go is concurrent. It uses concurrency. So we need to look at thread safety when we open an OpenAccess library and see, can we really access this in parallel? So there is a concept of multi-reader threads operating on one or more databases. if you read the manual, so here's a link if you want to read into that, it's on the web. And you simply have to set a session and then set thread use model to multi-reader thread use model to get this. Unfortunately, at least for me, it doesn't work. So if I try to, so my first experiment with that was, oh, let's try to read all the instances simultaneously, right? And I tried it, and it just core dumped. And so it's not clear where it's coming from. At the moment, I put a mutex lock around the reading operation and just use it in single thread use model. It works fine. The moment I do it in parallel, it breaks. So this is maybe something I need to bring up with Cadence to look into that deeper. Maybe it's related to Swig, maybe it's related to Go, I don't know. It would be great if it works, because that would allow really cool stuff in terms of, hey, I have a 7-nanometer test chip, which has billions of polygons. I can read this on 100 CPUs in no time. Right, that's the idea. Okay, let's look just at one little example how easy this can be. So for instance, if you want to read just shapes like rectangular polygons in Go through that Swig interface, what we have to define, for instance, I call it a PDFShape. It's a PDFShape, which the constructor, I give it an OpenAccess shape, and then I have an accessor which says, oh, give me the layer number, give me the purpose number, give me all the points, and give me the type, whether it's a rectangle or a polygon. And internally, on the C++ side, I simply store the OpenAccess, or I convert my OpenAccess shape into something I store here in a layer num, a purpose num, and some points, which is, again, my own class. So I'm kind of putting a layer on top of OpenAccess, which means, of course, that I store all the data twice. It's not elegant, as I said. If we figure out the access problems in terms of multi-threading, then we don't need to do this. And if we really want to spend the time to wrap it completely, then we are fine. But for this purpose, we really make it simple and just write a little small wrapper. So what else you need then? You need something which gives you all the shapes. So we need a function which I call, for instance, getShapes, which returns simply a standard vector of my own shape, which I defined. Right? So I would iterate then, I would do all this OpenAccess stuff here. Finally, I define a vector of my shapes, and then I open technology, get a block, get all the shapes, iterate through the shapes, push them into my vector, and then that guarantees me I can access it from Go later on. I have it in my own vector. So again, very simple. Now, what you have to do to make this compile, you define a so-called interface file. Here is a note. Typically, you call this .i, these files. In case of Go, you need to call it .swigcxx. If you would use C, you call it .swigc. Later, I'll tell you later why. But the only thing you do is you include your header, where you defined your classes. You include this standard vector.i file so that you get access to size. So if you deal with standard C vectors, that you get information about, give me the size of the vector, give me the first element, last element, and so forth, right? And then you simply define your own types here in terms of my PDF text, shape, layer, pins, points, whatever I needed. I need instances, and then that's it. Now, you typically have to write a really long makefile. I mean, literally that long. Luckily with Go, and it came a lot in the beginning with Go 1.1, I needed to write this makefile, and it was a pain. Luckily, we don't need anymore, because Go is smart enough to write this on its own. So the only thing we need to tell Go is, and so you have to kind of build a dummy.go file, I call it build.go, where you specify with some cryptic syntax, simply your C flags, CXX flags, your linker flags, so where's your OpenAccess installation, where are your libraries you want to include. And then the only thing you have to do is type go build and go install. That's it. it builds, if you have an option for the build command to see actually what Go is doing, and then it reveals that it creates a makefile that this long. And but Go is, in this sense, really nice, that it completely integrates with Swig. Okay. Now, how do we access then OpenAccess from Go? Again, since this library I just created with Swig was already installed, I can use it simply with an import statement, use OA. And then I simply say, OK, this was another function I didn't mention, but this I call this function, which gives me an object onto an OpenAccess database where I tell it where it is, the lib name, the cell name, and then it's of type layout. And then I call this simply this getShape function to get all the shapes, and then I can iterate through them. I can access data like the points and so forth. So really simple in this sense. And once we have it in Go, on the Go side, we can just do something with our shape in this case. So now let's talk a little bit about the web server. So what do we want to do with the polygon data once we have it on the Go side? One way is, of course, serving static images, but it's kind of boring. We would like to probably something with dynamic images, meaning we'd like to pan, zoom, maybe measure, or maybe turn layers on and off and so forth. So let's look at this a little bit more. So what I like to do also is convert our OA shapes. So since we cannot really do it on the OA side itself, so I convert these shapes into my own structure. I like to flatten these out. I would like to leave this on the OpenAccess side, of course. To get access through the hierarchies, there's ways of doing it in OpenAccess, I know, and once we solve the problem with multitasking, then I probably go back to this. But for now, I just push it in my own little OpenAccess database and flatten it out, store the polygons by layer, makes it easier to access. Once we have this, we render an image out of this polygon data where we assign line, fill colors, fill pattern, and then we somehow serve it through a web client. OK, how do we flatten something? Just if you're interested, it's very easy, or I came up with a simple algorithm. So what we do is we simply traverse the hierarchy recursive, so from the top node to the leaf node. And on our way down, we kind of build up a simple stack of all the transformations through all the instances you went. So if your top instance, your top cell has an instance which places some cell in an R90, you simply would record, hey, this is my R90, so you simply record this transformation matrix plus the offset vector, and so you go from instance to instance to instance until you are at the bottom, so your leaf node, and then you transform your polygon. So let me go through this flowchart. So you open the top cell again, so you initialize your transformation stack. So we work on a cell, so iterate over your instances. If you don't have your last instance, to push your transformation on your stack, work on the next cell, and so forth until you hit the last instance. Then you transform your polygon or shapes which you have in your bottom leaf node using the entire transformation stack and push it in this new database. That way it's flattened. And it's pretty fast because it's recursive. It does it really quick. There are probably other ways of doing it, but I decided to use this simple way. OK, so now we have something in Go. Now, how do we create an image out of that? Of course, if you're talking about high-level languages, there's always something where you can easily say, create image, dump in a polygon, done. Unfortunately, Go was a little harder because Go has an image draw library, but it only has one operation, unfortunately. Not even a polygon draw operation. It just has, you have a source image, and you can place a destination image into it. So that's pretty much it. So it's really basic. There is one further little detail here. They have a draw mask function where you have the same concept. You have a destination image. You put in a source image, but you have at least a mask you can do with something. And I explain in a moment why this helps us. So the idea is the following. You start with an empty image. You create a source image which has actually a pattern assigned to it, and that's the pattern you want to use to color your image. Like if you think about Cadence or any other EDA tool, they have this stipple pattern for fill and for outlines. So this is your fill color, fill pattern and color.
So that's what the user gets to determine.
That's, you could, right now I'm reading the display DRF and just read everything Cadence has, and I'm copying exactly the same definition. Luckily, I can just dump it in as is. I'm just, I can show you later. I can use the exact same definition of the stipples as Cadence uses it. It's just a matrix of ones and zeros for transparency versus non-transparency. And now comes the funny part. As my mask, I use now my polygon. So I simply say, this is my mask, so I kind of stamp out this little area, and then my result would be this. And I can then do a direct draw of the outline, so I simply do a set for every point of the outline, and then I get my polygon. And for every polygon, you do this, and you're done. I just want to point one little neat detail about Go, and this is this here, if you know this. So if you look at the definition of the function, this draw mask function, it expects as the mask an image. But here we give it actually a polygon. So what is this? And this is something which is called a Go interface type. And that's a really interesting concept. You might know it from other languages. So you have a polygon. So let's say our polygon is a simple struct which has a list of points. That's our polygon. It has, of course, more like layer definitions and so forth. What this draw mask function wants, it's an interface type, meaning everything which has these three methods defined is called an image. That's as simple as it is. So if I simply say, okay, I define for my polygon three functions called color model, bounds, and add, then it's an image, or it becomes an image. And I simply do this by saying, okay, color model, it's easy, I just return the default color model. Bounds, I simply return the bounding box of my polygon. And add, I simply decide whether I'm inside or outside. And then I'm returning an alpha of 255, meaning non-transparent versus transparent, and that's it. And so you can dump into this function whether it's a polygon or a path or a rectangle or whatever it is, as long as you define these three functions, you didn't need to worry. And that's called interface. It's a pattern, and it's really makes it really easy. Okay, now web client. I found something interesting and was thinking about, there's something called Leaflet. It's an open source JavaScript library for interactive maps. So what the hell have maps to do with polygon data? But actually they have quite a bit in common. So first of all, there's lots of data. So the further you zoom in, the more data you get in a map typically. And if you notice what happens if you zoom into Google Maps, you sometimes see these empty squares popping up. And so this is a concept they call tiling. And what in the background happens is every square is a separate process and gets rendered differently, so concurrently. And so the map application is actually a good map, not a a match for dealing with polygon data. And luckily, this Leaflet Java library is open source. It's free, no royalties, so you can use it. It's pretty nice. It's well documented. It's well supported. And it's really easy to set up. You just need a few lines of JavaScript code, and that's pretty much it. There's one problem, though. Map coordinates are not really XY, so Cartesian. They are kind of longitudinal and lateral, and ooh, that's nasty, so we have to somehow convert this. And then what happens to our layers? We want to display metal 1 versus 2 versus 3 and not have just one single map. Then just a few words about tiling. So what these maps like Google Maps do is in your zoom level 0, where you see the entire world, you get one image back. So there's not a lot because you can't see. And this is the same if you would open a full reticle chip. I mean, you don't see much other than color. It's colorful. The further you zoom in, the more titles you get, and the more detail you get. And that's the same problem we have actually here with our polygons. The further you zoom in, the more details you get. And we can use this behavior pretty well. Okay, so now we need to define, of course, a request handler in Go. As I said, the web server is one line of code. The request handlers are 2 more lines. Request handler is, oops, sorry, again. So the request handler would react to if you have an an address to call your web server. I decided to go with a view handler and a so-called tile handler. The view handler does the following. It will kind of initialize your process, meaning it looks up the database. So you could think about, you give it your host name, some port, then view, and a lib name and a cell name. So you look up the OpenAccess database, read Flatten the database into Go space. You create a cookie so that you can identify your session, so that multiple users can access even the same design. You store this into a connection hash, and then you simply return an HTML, some HTML code which initializes the web client, so this map client with some other initialization you have to do. The map itself will then, for every tile, so every zoom level and tile, and later on few more words about this, it will send a request to the server. So in this example, tile and then zoom level X, Y, and so forth. I'll explain later. So, and the tile handler simply, what it does is, it simply says, oh, give me the tile for that zoom level, that X, Y, and that layer. And then it sends an encoded image back. Okay, what happens if you start this application now? Of course, to compile it, you simply type go build, then you get a nice executable. You call it, and then it says, I'm using 8 CPUs. It automatically grabs whatever CPUs you have on the system. If you have 100, I can tell it to use 100 CPUs. And then it waits until someone says, request a view. And then it starts, okay, reading OpenAccess. So that's the SWIC, that's a message coming from C++. And now I'm reading in a little test case where I say, okay, I found these shapes in these layers. I flatten them out. This is my bounding box, and this is my cookie I'm setting to identify the session, and my database units are 4,000. And once the user starts zooming in and zooming out, you get all these tile requests for different zoom levels and so forth. Okay. Now the JavaScript, there is something nice in Go. Go has a so-called template package, meaning you can more or less replace variables within a template with actual values. And we use this simply for defining the code you need to set up your map or this leaflet application. So it looks the following, that you simply have some HTML where you define your header, body, CSS, whatever is needed. Here, the only thing you have to do is defining URL in this kind of format where you say, okay, this is the URL, Z stands for zoom, X for X, Y for Y. Style ID is something I define, which is in my case a layer, and then tile.png. Then comes something like parentheses, parentheses, dot tile layers. This later on gets replaced by Go with whatever tile layers is. It's just some JavaScript code. So all these are variables which get replaced with some Go later. For instance, we can define, luckily in this map application, there's something like a Cartesian coordinate system which you can use instead of a map coordinate system. And here you simply define a transformation which then simply, instead of dealing with pixels, you suddenly deal with micrometer. So luckily this works really nice out of the box. You don't have to do a lot. Okay. As I mentioned, just here, yeah, this is the URL. So for instance, for the template parameters, like in this transformation, you simply set then in your Go code what the transformation is. Since we are dealing with little pictures or little images which have 256 by 256 pixel, so you simply divide this by your maximum bounding box size in one direction divided by your database units per user units, meaning if you would measure on your screen, it would tell you, the map would tell you, hey, you have micrometered. Let me see what else. Oh, with time. Yeah, okay. Okay. Let me skip over this because I think it goes into too much detail. Let's just show you the result a little bit. So on the left, you see a known EDA tool where I simply draw a via stack from metal 1, via 1, metal 2, V2, V3, right? I used, and on this side, you see the web server. You see how it automatically popped up all the layers. So you can essentially deselect and select layers. It uses the same coloring since we are reading the display DRF. It looks exactly the same. And you see these little green boxes. These are my tiles. Of course, in this case, it doesn't make sense to have 4 tiles because, I mean, you would only deal with 6 polygons, right? But imagine you read something bigger, then it makes very well sense that you have. Or even here, if you zoom into zoom level 4, you see how many squares we have. But nevertheless, it works pretty nice. And every of these is rendered on a different CPU. And if you call the web link, it's instantaneous. And you don't even notice. It's there. That's the cool thing. There's another nice thing about this leaflet. There are so-called plugins. For instance, there's one, and great, it allows us to measure. So you simply install it. It's just downloading it and initializing it, so 1 line of code, literally. And then it allows us to just measure distances in micrometers. So in this case, I cannot even read it, 22 micrometers, so I really designed it, of course. But it gives you, every coordinate you see is micrometer. And of course, you can now really become smart and say, okay, the moment some user presses down or a mouse click, you can have a handler registering the mouse click, and then you can send something back to Go, say, give me all the polygons which are closest to that point, and then you can say, okay, this is your closest point. You could snap automatically to the next closest polygon instead of just measuring. So because sometimes you want exact measurements, right? So you can essentially blow up the system quite a bit to do accurate measurements and so forth. Here, real little structure. You just, again, it comes up instantaneous, and it gives you then all the layer. Another cool thing you can do is like of annotating it with, your cadence pins. This is why I was reading also cadence pin information, and you get these little markers here. And you simply click on the marker and says, oh, this is your pin N2, N1, C1, C2, for this little snake and comp example here, which allows a lot of, you can put now in this map application a lot of artificial things which help people understand how this thing was designed instead of just looking at layout, meaning identifying, for instance, how this thing is wired together, where are my pins, what is the function. You can play a lot with it. Okay, application areas where we plan to use something like this is for our design for inspection infrastructure and design a characterization vehicle infrastructure, mainly to visualize cells, overlay DOE information with it. One idea is, for instance, you could do side-by-side comparison and even animations if you, for instance, deal with misalignment experiments where you purposely shift polygons. So you couldn't simply do instead of showing 20 pictures where you do a misalignment experiment, you can query the DOE database saying, hey, what is the DOE in this thing? Okay, it moves the polygon from minus 0.1 to plus 0.23, and then you could animate this in your actual
Mass misalignment.
yeah, mass misalignment, exactly. You could overlay network information because that's, especially for DFI or electron beam experiments, you want to see what's grounded versus not. And so you could overlay some network information, which simply allows the user to see what is connected to what. Or some automatic web-based documentation. Instead of looking at static pictures, you have now the ability to just zoom in and so forth. It would for sure help people to understand designs way better. Another thing would be nice, instead of, like, if you open a full chip design, instead of seeing polygons, it doesn't make too much sense, because at that zoom level, you don't see much anyway. But you would rather navigate a huge design in terms of functional levels. So show me where's the SRAM block, where is the processor core or something like this. And so you kind of abstract into this view functional blocks, and this way you zoom in, navigate a huge layout, and it makes it for sure. Because the faster, at the end you only want to see polygons if you're down in the standard cell row level, and there it's okay to show polygons. But above that, functional views might be way better. Another thing where our people struggle a lot, you typically design in terms of design layers, right? But mask layers are Boolean operations on these design layers, so they don't really help you if you see A and B layer or whatever fin layers without a cut in there. So you want to actually do the cuts and then see how it comes out. So you overlay this with Boolean operations and give the user a way of switching between mask layer, design layer, and so forth. So some outlooks, some limitations, future work, and final conclusions. So full chip layouts, as I mentioned, opening a design, for instance, 7 nanometer is incredibly slow, if you, especially at a full chip level and want to see something, because the time it takes for something like Cadence to go through all the hierarchy levels and parse everything is just incredibly slow. So I tell everyone I have designs, it takes 2 hours to open a cell. So I go to lunch, and then when I come back, it's maybe open. So we need smarter ways of looking at layouts. We also may be thinking about, let me see, this comes later, sorry. You overlay useful information. As I mentioned, we want to maybe overlay simulated layouts. So how do they really come out when they are printed on the mask? Or we want to extract some attributes, which we want to overlay, like critical areas or other interesting things, network information, even 3D views would be really helpful, or cross sections, because sometimes it's from polygon data to understand what the function of something is really hard without additional aids. In terms of memory usage, what I was showing you was not optimal in terms of memory usage, because I'm kind of doubling or even tripling my memory because I have it in OpenAccess. I convert it through SWIG into Go, and so there are some inefficiency, but they can be solved working with Cadence on figuring out why the multi-threaded mode doesn't work or why it doesn't work for me. Maybe it's a Go problem, I don't know. So yeah, once we have this, I could move some of the functionality back, of course, into OpenAccess, just leave it there, and really use multi-threading in a native way, more native way. OpenAccess for sure can be improved in terms of performance. I'm not sure what kind of projects are planned specifically in regards to multi-threading performance, because, as I said, newer technologies, we all will die at some point just by waiting. Conclusions. So OpenAccess can be used with almost any language. That's a good thing. You can just, if you have a language, I'm not sure it works with Fortran, but there might be a way. SWIG is a cool tool to just map any language to any other language. We do this, for instance, in other areas where we say, okay, there are cool or heavy computational problems where you might have something written, a genetic algorithm, which is slow, really slow if you do it in something like Ruby, where if you do it in Go multi-threaded, it runs in milliseconds, in factor of 1,000 faster. So in these cases, you would use SWIG to just bind a compiled language to a scripting language. A web-based OpenAccess viewer is really feasible. I can view relatively big layouts without any problems, even at this prototype state. I'm really surprised that it works nice. Of course, you could come up with different ideas. You don't need to render images. I tried, for instance, just pushing back directly SVG, because SVG is already polygon data. It can be zoomed natively. You don't need to really have this infrastructure of sending new pictures if you're at a different zoom level. The only disadvantage of SVG is it doesn't really support arrays very well, so you need to flatten out your arrays. It has something which is called a pattern, which you could use, but web browsers behave differently. So on some web browser it looks good, on others not. So this is why I said, oh, maybe we should go for now with native images. And as I mentioned, cells can be served using this web browser with almost no delay. It's so definitely something feasible. Okay, that's my talk. If you have any questions.